So, see, it's just his paper. So, so did he go through this paper at all? Okay, that's good. This will be a short class if he already went through it. It's like, anyway, back when he was in India, so the stuff he's doing now is a little bit less kind of with this class, let's see, where were these guys? Oh, Pune. Okay, so Pune is near uh, Mumbai, or how do you pronounce that? Bombay. Mu, how do you, Mumbai, yeah. Somehow I couldn't get that in my brain right. Mumbai, yeah. So if you go, I guess I haven't been there, but if you go inland from Mumbai, there's a landform, there's like mountains, it's actually like the largest volcanic thing in the world. And they think that it had something to do with, like, the asteroid had to do with the dinosaurs disappearing, but this formation supposedly could have killed the dinosaurs too or something. It was the largest volcanic explosion ever. So this huge sulfur stuff got into the atmosphere. Anyway, this is like gorgeous, like mountain area right now. Pune's in that. It's kind of like the polymer. It's like a polymer center in India. It's not far from Mumbai, but so it's a good place. But, anyway, so he's from there. I don't know this Lele. Maybe I've heard his name before, Lele, but anyway, so this problem, there's a few other papers. So ultra high molecular weight polyethylene. Did he talk about that at all? Or all right, so I talked about it before I left though. So it's basically take polyethylene, which would normally be like 100,000 grams per mole. And then I mean it has broad polydispersity, like MW over MN is like 16. So like if you anionic polymerization, that's 1. So 16 times broader than a monodispersed polymer. And it's got multi-modes in it too, high density. So, and then so 100,000, and you amplify that by a factor of 100, you get like 10 million or something. So it's 10 times longer chains, right? And then the entanglement molecular weight is something like 5,000 grams per mole, I think. So basically in 100, you have 20 entanglements per chain. That gives you all the viscoelasticity of it. But if you have this ultra high molecular, you have 200, or you have 100, what did I say? 20 goes to 2,000. So each chain has 2,000 entanglements in it, I guess. If you calculate by all right, so that's a lot. So basically you can't extrude it. Once you get to that, it's a rubber. Right? If you try to extrude that above the melting point, it's just won't move. It's a solid. So to make things with that, you grind it up into a powder, or you have a reactor powder where you made it. You put it into a rotational mold, and like we went out to Lyondell, they have a few of these rotational molds. Apparently it's pretty cheap to make things with those. But anyway, you just rotate it in the mold above the melting point, and it coats the sides of it, and it makes a part. Like that's how they make these plastic climbing toys, some like jerry cans and stuff. And they make a lot of like kind of truck bed liners and things like that. So they make a lot of these kind of things that are hollow, like kayaks. They make with rotational molding. So you can make, anyway, truck bed liners need to be like abrasion resistant. And this ultra high molecular weight stuff has super abrasion resistance. So that they use it for that. And catalytically, I don't know how they figured out how to do that, but basically, I mean, you have to get rid of the termination step. That's the issue. So if usually some water or oxygen gets in and kills the reaction, right? So basically, I don't know exactly how they make ultra high molecular weight, but they've gotten rid of the termination step of the polymerization, so it just keeps going forever, right? And they just let it go forever and make it as big as they can. So, and also like if you so you can't extrude it as a melt, but you can put it into a solvent and swell it, and then like dichlorobenzene, heat it up to like 80 or 90 C, and then you can make a gel out of it. And when you make it into a gel, if it's dilute enough, there's no entanglements, then they spin that gel into a fiber. And then when you do that, you get perfectly aligned chains that go on forever, and you get almost the strength of a covalent bond, which is the strongest thing per gram, right? So you could actually, when they talk about making space tethers, that's a real thing. So people wanted to make a space tether so you could take an elevator into space. So you have a satellite floating around and there's a rope that comes down, right? But the only thing strong enough to do that is this stuff, right? So this is like part of the space tether thing also. But you can also make a bulletproof vest with it and make sails for racing sailboats that don't rip. You know, when you get a lot of torque under a fabric. So there's a couple, and then hip implants, because you don't want to have little chunks coming off, and then biologically it gets built up around it, and then you get problems. That's why you have to have a hip replacement after, like you get it replaced, and then later it only lasts like 10 years or something. And you have to replace it because of that problem. You know? So nothing else really wears, because the titanium ball, ultra high molecular weight cup, you know, those two together. So anyway, so there's a few uses for the stuff, and then he's trying to have another use. So the idea is like, this stuff has a much higher modulus than high density. So basically, if you could put in a little bit of this, then these long chain fibers would kind of make a fiber reinforced, except it would be the same material. So it'd be a molecular reinforcement of the high density. So you could see something interesting with that. Anyway, the problem is it's got a really high viscosity compared to high density, because it's going to go with molecular weight to the 3.4 power. So if you do 100 times the 100 times the molecular weight, you get whatever a million times higher viscosity, and maybe more than a million times higher viscosity. So it's a rock. Basically, you put it in. If you put a rock in water, it just kind of doesn't mix it, and you can't mix it with the viscosity difference. So anyway, to get around that, and he's saying it's because the chains are entangled with each other so much. So they figured out a way. Anyway, he commercially gets this DPE, which is unentangled ultra high molecular weight polyethylene. So get rid of the 200 entanglements per chain, or 2000 entanglements per chain somehow, and then you get this DPE. Then that they claim can mix with high density polyethylene, right? But the problem is, so then they run into another problem, right? So actually this other paper talks about how to do that more or less, and then this is a follow-up paper. So there's a problem, like you put it into a high shear mixer, which if you went to Lyondell, we saw that mixer. It's basically an extruder that's got mixing elements in it, so that you get like backflow. So you have segments where you have backflow, and then it's got what do they call them? It's got like gear elements that kind of super mix the stuff. You know, it's a high shear mixer, they call it, like Kraus Maffei in Kentucky, but. Anyway, so that's what they're using, these kind of industrial mixers to mix these two things. Anyway, so that's kind of the idea. So, but the problem is, like, so say you put it through that, and then maybe you get a higher modulus. You say, oh, it worked, but they want to see like how much mixed, and there's no way to tell exactly how much mixed, right? So what they're going to do is get the rheological signal from it. So somewhere here, so they have curve fits to the, so these are he talked about oscillatory shear, right? The measurement where you oscillate the cone and plate thing. So that's what they're doing here. So they have G prime, G double prime, there's a crossover, and these are for, let's see, these are the unentangled ultra high molecular weight, so the DPE thing, right? And then from that curve, they figure out a way to get the molecular weight distribution, because you can't exactly, because you can't take the stuff. So a GPC, like, you're going to force a polymer through a gel under high pressure, and then the big things come out first, small things come out last. But if you stick this stuff into it, you destroy, because it's like putting a rock into it, a molecular rock. So basically, you can't use a GPC to get the molecular weight on it. So not a, yeah, GPC, yeah. So anyway, he does a, so he's going to get the GPC he's going to get the molecular weight distribution curve from the rheology, right? And he does that with this. He's got a model here to do that. Let's see. So he's got a model that it models the time-dependent modulus, okay, with the molecular weight distribution, which was WMW. WM is the molecular weight distribution. So this function, this is called the DR model, which is like this DR stand for. It's like the tube model with the relaxation of the tube thing. So I forget what D and R stand for. Here, double reptation. So it means like he talked about reptation last week. So he's going through a tube, and the tube also is relaxing. So it's a double relaxation thing. In other words, it's a relaxation for the chain to go through the tube. The tube is made up of chains, so that relaxes too. So it's a double whatever. So the DR model, and then this business you don't really need to know about. It's basically some of what he talked about, like how. So that's where this equation comes from. This function, right? So it's got a molecular weight distribution in it. It's a time-dependent modulus. It's basically, if you follow the Cox-Mertz rule, you can Fourier transform this into the frequency curve. And then you can get the molecular weight distribution from the G prime, G double prime. Right. So, but in order to do that Fourier transform, you have to go from 0 time to infinity time. Right. So there's a problem always with doing Fourier transforms. You're doing an integral of exponential I times the thing dot the thing, so time dot frequency, imaginary, and you do an integral of that. But the integral has to be over a range, and the range has to be from 0 to infinity, or it doesn't work. You can't truncate it. So you need to have a function that would extrapolate your thing to 0. You can't actually measure it at 0 time. You can't actually measure it at infinity time. So you have to have a function that predicts infinity and a function that predicts 0 in order to do that integral, right? If you really want to do it right, or you can just pretend that it works, whatever. So anyway, so that's what he's going to do. So basically, he transforms this thing and he gets a function in frequency for that, and then he can, from the frequency thing, he can get them like a weight distribution. So you think, well, that's never going to work, but he kind of does it. He demonstrates that it works. He does it first for the high density. So the molecular weight distribution from Gen X fit from the G prime, G double prime fit, and then experimental from the gel formation chromatography for his high density stuff. Right. And then he has, somebody had measured, so one of these is for high density. I think A is for batch number 1, batch number 4. These are both for the, and then the data, the GPC data is from a paper. It's from some other, he doesn't measure that. But he does it also for his high density first, I think. Although I don't see it right now. Yeah, this is molecular weight distribution of high density resin from the table. And then so the blue is the high density, the black is this viscosity, intrinsic viscosity number. Right, so this is just characterizing his the high density thing. So that's the way that works. Okay, maybe I mentioned the intrinsic thing before, but the moment you just do that. So it's kind of a simple paper, but it's pretty nice, it's a nice paper. So that works. Right. So let's see. So we have the intrinsic viscosity. So we have like the viscosity. It's going to be the solvent viscosity times 1 minus this intrinsic viscosity times the concentration. Right. So this thing has units of 1 over the concentration. It's basically 1 over C star. This intrinsic viscosity. This is the solution. Like if you put a polymer into solution, that's the concentration of polymer, and then you get this 1 over I star, which is going to be the mass divided by the volume right? So this thing has units of volume per mass, not viscosity, even though it has a viscosity symbol. No. So it's really 1/pi star. So then if you say in terms of so the size to the dimension is the mass, and the volume is a size cubed. That means that the volume is going to be mass to the 1 over the dimension cubed, right, divided by the mass. So that means that this thing, that means this intrinsic thing is going to be the mass of the thing times 1 minus 3 by the dimension of it. So if it's say it's a Gaussian chain, and then in this power here is going to be minus 0.5, right? And say it's a good solvent chain, and dF is 5/3, so that's 9/5. So you have 9/5, and the 1 is 5/5, so you end up with 4/5. That should be that should give you that the intrinsic goes with a mass to the minus 4/5. It's 9/5 is bigger than 5/5, so minus 4/5, which ends up being 0.8. And say this is 1, say it's a rod, so 0.8 would be that's good solvent. 0.5 would be for minus 0.5 for this power would be theta solvent. And if it's a rod, and that's 1 minus, so it's minus 2 for a rod. And that's kind of your options. And that's a simple way to do the options. You can get any number you want, but basically that's kind of what it should be. So here he gets 0.7 out of this. This thing he's getting minus. He's getting the intrinsic goes with molecular weight. See, is it minus or plus? This is the it's let's see, did I do this wrong? He's getting plus 0.7 on this thing. Plus exponent of 0.7. Intrinsic goes up with molecular weight. That's true. Did I do this wrong? This looks like intrinsic because I did this wrong. This is the C star thing. Right? Let me see. What did I do? Let me do this over again. This thing is going to be the volume per mass. That's true. And then oh yeah, so it should be the volume is R cubed. R is 1 by dF, so 3 by dF. It's mass times 3 by dF minus 1. I'll do it backwards. So it's just the negative of that. Plus start. Should be plus. Should increase with molecular weight. So anyway, he's getting 0.7, which is kind of in the range here between 0.8 and 0.5. So whatever that means, basically it should be 0.8. So it's a good solvent. You know, it'd have to be a good solvent for this. Anyway, so that's kind of what, and it's straight lines. That's pretty good. And it's a log plot, hopefully. Yeah, log of intrinsic versus, and this is a log scale, so it's a straight line. That's good. And that means that this whole scaling thing works. So anyway, that's one of the questions. That's why I mentioned that. But and then he uses, in order to get this curve, he uses this Jex function. Right. So I've never seen this before actually, but here it is, and it predicts the shape of that curve. So it makes it easier because otherwise you just have a bunch of numbers, right? So he's got a function. He needs a function to plug it into this thing, wherever that equation WMW to get G of T, right? So he needs a function to do that. So then he goes. So if you have a blend of things, you want to know what's the composition of the blends, then they can take this equation that gives you that same function to get the GT as a function of molecular weight distribution. So first he has to get the molecular weight distribution of the DPE using viscosity, using the G prime, G double prime. So he does that. Then once he has that, he goes to the blend and he wants to know, so the main thing he wants to know is how much of the DPE got into the HDPE, right? To get the composition of the blend. In other words, I put in a gram, did it end up with a gram in the mixture, so it reinforced the high density with a gram, or did it end up with a half a gram or none, right? So And he's claiming he can get that by looking at the G prime, G double prime and going through this routine. So it's a little bit of an involved routine. Yeah. The viscosity is going to be the loss modulus divided by the frequency. So G double prime by frequency, and it changes with frequency because it's a shear thinning fluid. So it's going to have a power law decay. So it's going to be flat at low shear, and then it's going to go down. So G double prime divided by omega gives you the so basically you need like you need the tau for the relaxation, and you need the G naught to get everything. So if you have two numbers, you can predict all those curves theoretically. I mean, it's kind of integrals you need to do. But basically, those two numbers will give you the compliance curve, the viscosity curve, and the modulus curve. They should all be related to each other. Like continuum mechanics does that for you. So basically, you can do any measurement. You can do a creep measurement. You can do a compliance measurement. So you let the stress, you let the strain rule and watch the stress. Right, so you do a fixed strain and then watch the stress. I guess let's see, stress strain. So no, normally you do, yeah, that would be a modulus. That's like a G. So if you let the strain rule and watch the stress, that's G. So you're oscillating. That's fixing the strain, and then you look at how the stress responds. That's where you get the modulus. If you do the opposite, you fix the torque on it and watch the strain, then you get the compliance. And then you can also get this time dependent by just putting a weight on it and letting it kind of droop. Yeah, or stress relaxation would be the modulus term form of that. So stress relaxation, I pull it, then I watch it. I watch the stress drop. So I'm fixing the strain, and I watch the stress change with time. Or I can fix the weight on it and just watch it droop. So the Cox-Mertz thing says that it's a rule, meaning it's not proven. Those things are related to each other. The frequency measurement and the time measurement you can get one from the other. So there's a lot of little weird things here, nuances that are kind of important, like these time dependent measurements and the frequency measurements. The frequency are much easier to do, especially when you're doing that tensile measurement. I mean, if you really want to get it to go forever, you're going to run out of space, It's basically there's some limitations to it. The frequency, you can do anything you want until it slips at the probe. Yeah, expand the frequency range. Yeah, so you cool it down or you heat it up, and that's going to give you like 3 decades every 10 degrees or something in the frequency, because exponential to the temperature. Um, no, I don't think so. Because look at his data is like 2.5 decades. That's the frequency. Oh, no, the molecular weight's many more. But his data's, oh yeah, he does do it because he's got like 2.5 is about what you can get at one temperature. So then yeah, he must do a time temperature to get these. He must mention it in here. So the trick is like the frequency thing, you can use the WLF or just an Arrhenius function to do that shift. But this function, so you also have to shift in the Y direction too to get these to match up. And that's more of a mystery. Like people just do it. Sometimes they don't say they did it. So and then some people have gone about what that value would be to shift it that way. So anyway, you have to shift it that way, kind of an arbitrary amount. And that people sometimes will plot that shift factor versus temperature too. So you can have WLF factor and then the shift factor here. So if you actually do the measurement, you're gonna have to do that shift. So don't be surprised. Like it's not wrong when that happens. I mean, it's just that it's ignored generally. But I think he's done shifts on this. I think he would just use WLF. I didn't ask about that or anything. Time. Oh, see, time would be in it. He says it. I don't think there's a supplemental to this thing either. He doesn't mention time temperature or anything, but it looks like he did it with the frequency range that he has. Anyway, so he does that, and then he basically is just going to get the composition of it, like the weight percent DPE he gets here, and then he shows this plot. So it's a little bit involved. Like I don't expect you to be expert at what he does. Like some of it I don't follow it exactly, but basically just kind of like the framework of what he did. That's the most important part. And then that they achieved it, like this actually kind of works. I mean, you might want to think about what problems could come into play in this thing. But like one of the problems he mentions early on is that, well, when you try to mix a high viscosity and a low viscosity thing, they don't mix very well. Like if you think about, I don't know, if you try to, anything that gels up you can't mix once it gels in a solvent, It's kind of like when you're trying to mix like honey into water, it eventually melts and goes into it. But when you first start stirring it, nothing happens. Like you just have globules of honey and all the torque goes into the water and the honey isn't sheared at all. So I guess that's kind of what's going on. You have these globules of this ultra-high molecular weight. You're putting into a high intensity shear, but like the globules aren't coming apart at all. So there's no, so this business of mixing, I guess, so anyway, or let me just finish this. So he's got this issue, like he puts in 1%, right? And then this is the amount that he put in. X is what he got for his measurement, and this is what he put in when he actually weighs what he put in, right? So if you put in 1%, almost all of it goes in. That's good. Then as he adds more, it's a diminishing return. Like, so eventually he'll get to like 6%, and that's all he can get. He can't, no matter if you put in 100% or not 50% of the ultra-high molecular weight, he'd still only get like maybe 8% in the thing, right? So something's going on with that. And it could have to do with this thing about the honey and the water thing. I guess that's what I'm thinking. I asked what. So let's see, that's figure 8, 9, right? So it's similar here. Like 9 shows the fraction loaded decreases when increasing load. What was like? Why is that the case? So so it is like honey and water. They're perfectly miscible, right? No, it's just going to go in. It could go in, but they never mix. So you can imagine if you had like cross-linked honey, or say like one of these hard candies or something, you put it into water and you stirred it. No matter, even if you put it into a high intensity stir, maybe you'd never get 100% of the hard candy in, not within a reasonable time. And these things like honey, like sugar diffuses pretty fast, but these things are going to diffuse on the order of like hours, right? So it's basically there's a limit to like how much of the stuff you can get in, right? So anyway, so I guess that's my answer to that. You might have a different one, but there's a discrepancy. He doesn't I mean, this is the only flaw probably in the paper is like, he doesn't note that and like say why it happens, why it is like that, or like postulate why it's like that. So I asked that, but that's, I think anything you say will be good, but basically, I think if you think about like trying to mix things, so, and then there's something, I guess there's something also missing from this thing. I'm stuttering. It's like Joe Biden or something like rubbing off, but not that I listen to the thing. But anyway, so if you mix things, so there's this called dispersive and distributive mixing. Right? So and then this odd things that happen with mixing, like this. So you have the Reynolds number, and if you're generally like less than 2,000, the Reynolds number, so it's going to be the pore size, the viscosity, the velocity. It's like, so for thin pores, you have a high Reynolds number, and high viscosity gives high Reynolds number. So if you have, let's see, that's not right. And high velocity, high viscosity with high Reynolds number. That's true. I think it's like that with D at the bottom. So let me just check it for a second here. Let me get this right. I should know this, but yeah, L's the, yeah, that's right. Yeah, I knew I had this wrong, but see, the viscosity and the viscosity's below, right? Thanks. So you're right. I just wanted to check to make sure that you were right, I guess. Right, so the viscosity is down here, velocity, and then the gas. So if you say you're running through a capillary, the band would be. So if you have a really thin capillary, so it's a problem like they have MEMS devices to do biomedical stuff. Like you put your blood in, it goes in, you have to mix a reagent with the blood, and then you can't mix them because the D is too small, right? And because of that, you can't get any real like distributed mixing. Right? You can get dispersive mixing because you can get diffusion across the flow streams, and you can't mix this stuff. It's a problem. Like they want to have these instead of doing lab tests in a lab somewhere, and the blood samples get mixed up and then somebody dies. So they want to do the testing out with that. So they have like a little MEMS device that'll test it. But you have to mix the reagents. This is the main problem with MEMS testing on site. You can't mix the thing. So anyway, there's that issue, and then there's the high viscosity is going to lower the Reynolds number. It's like, so if you're doing this measurement for laminar flow, you want to have, anyway, so laminar flow is a funny thing. It's like reversible. So if you're below 2000 and you mix the things, then you get this, it'll look like it mixed, I have a picture of this somewhere. It's in a few places, but it's probably on the internet here too. Laminar flow video example. Yes. Yeah, here's a good one. So you see, like, so when you're in this condition of laminar flow,
thing in red.
and mute them too. So he's putting in, this is corn, what is it? Corn syrup. So it's viscous. So high viscosity means you have a low Reynolds number. It means it's going to be laminar flow. It's a pretty big gap. So that would give you a higher Reynolds number. And then it's low viscosity. So it's just got a cup and a cup. You can make this yourself. Anyway, so you spin it forward and it looks like it mixes pretty well. Da, 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 da. So it's mixed, right? You say that's pretty mixed. Then he stops. So it's only mixed like a deck of cards. Like you slide the cards against each other, but you can slide the thing back into a deck, right? So you don't think you can do that, but actually you can do that. And it's pretty easy. We did this, I had this as a project once in thermal or something. People did this. They made their own. So it looks like it's reversing the video, but it isn't. Like you can actually reverse that mixing. So that would be like dispersive. That would be, well, the diffusion that occurs between the streams is dispersive mixing. Distributive mixing is if you could actually like move the pieces around, like the chunks of the pigment around, and then like rearrange them. Like you have checkers on a checkerboard and you change the red and black and mix them around. So that's distributive mixing. Dispersive means that you break the thing apart by like diffusion. So you can see some diffusion happen, but you get exactly, except for the diffusive thing, like the gradient is totally reversible, right? So anyway, so one of the questions is about like this idea of dispersive and distributive mixing, and in a high shear mixer, you get distributive mixing supposedly. And then how is that going to, so dispersive is going to be like breaking apart these ultra high molecular weight polyethylene chunks. Is going to be like rearranging the pieces, right? So the question is, let's see, there's a question about this. Here, mix two kinds of mixing. He doesn't mention this in the paper, but he should probably, I mean, it's something that you should think about when you're doing mixing, right? So I thought I'd bring it up here. Same thing I said, laminar flow, blah, 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 high shear mixer. So like two kinds of mixing, maybe Google them. Like you just Google mixing. I should put a link in for that, but There's bound to be a wiki page on this. What did I just do? I did something weird. Yeah, this shows, I mean, you can find this. I can put up a lot of links to this, but I'm looking for a wiki page though, let's face it. At some point you just want wiki. So yeah, this probably shows it here somewhere. So just think about like what's going on here and like how that is a dispersive, is this mixer that is using this high shear mixer actually the best setup for this mixing problem that he has? Right, like so he's using an industrial, like if you guys had gone to Lyondell, you would have seen this, but there's like extruder, it's got all different sections, parts of them are backflow, and there's gear mixers in it, so it's super high shear, narrow gap, right? So basically the narrow gap means you're going to get more laminar flow. So you have this narrow, you think you're going to shove all the stuff through a narrow gap with a lot of energy going into it, and you get laminar flow. It's not mixing at all. It's mixing in terms of making it look like it's mixed, but it's not really mixed, right? So these are the kind of issues that you run in when you try to mix things. It's not just, this business isn't just true for polymers, it's true for, and everyone in industry is mixing stuff. You're always going to be mixing things, no matter what, if you're in cosmetics or in whatever, right? So everything is mixed. So anyway, and getting a good mix, and what do you mean by a good mix, right? So is it going to be, so how are the chunks of the things being distributed in it? So mixing is a big deal. I mean, and when you actually go to do something, mixing is going to be like a issue that you want to look at. So anyway, what else we got here? So is that business? This just asks you to kind of go into that. So Reynolds number is one number that's kind of interest to me. And then the other number, even though I couldn't define it right, the other number is this Deborah number, which is important to polymers. So that's a ratio between your process time and the time that polymer materials have a time associated with them, this relaxation time. Like in other words, you have the plateau and there's a cutoff, says a time, 1 over that frequency is a time. And the shear rate, so you can say like that whole viscosity curve is really just looking at where the Deborah number shows to be 1, where your process time, your shear time matches the material response time, then you start to see this shear thinning behavior, right? So you want to look at like, what's the speed of my mixer versus the relaxation times of my material. And the relaxation time of the ultra-high polyethylene is going to be like a day, right? So you'll never see that tail over for ultra high. And then the other one's going to be maybe like whatever it ends up being, like a couple seconds, 10 seconds or something. It's like 0.1 hertz or something to tail over. So it's kind of a 10-second relaxation time, right? So anyway, so the Deborah number, like for the 2, is going to be off by a factor of, 1,000. In other words, so the processing conditions for ultra high molecular weight are like drastically different than high density by a factor of 1,000 difference in time, right? So how does that pile into this distributive? So it's a complicated question if you try to think about the whole framework in this problem, which he doesn't dwell on. Like he just says we want it, like he's practical. He just wants to see how much mixed. Like, but there's these other issues that should be thought about. Anyway, so you can kind of, I think you can just Google Deborah number, and what Reynolds number is better than I do. So you can kind of figure out like how this thing fits together and just think about it, And then while you're on a beach in Florida, right? Or at a bar or something. So it'll be a topic of conversation. So, but anyway, so then he goes through a scheme here. He actually spells this out step by step, how he does this whole operation somewhere in this paper. Let's try I can find it. But if you read it, just kind of try to highlight that part, and then just that answer is just like give the steps that he did, and he gives them explicitly in here somewhere. Terminal details, I think it's after, it's in the results and discussion, figure the dynamic modulus, somewhere he gives the exact, it's just a short part of a paragraph, he gives the exact steps of what he did. So I think you'll have to find it. I don't think I can glance through, because I found it once, and then I went back and found it again, but it's explicit. He gives like, he doesn't label them 1, 2, 3, 4, but he lists them in terms of 1, 2, 3, 4. So just try to make a 1, 2, 3, 4 thing about what exactly he did, for this one. And then why do you, if you do that, then you'll know why you need the molecular weight to fit the SAS data to get the percent that went in. Right? I mean, it's explicit what he says. And then the Cox-Mertz is this idea. You can Google that too. Like that's got a wiki page. I always want to put a T in that. So there's a wiki page for that, I think. So that's kind of the governing rule for everything these rheologists do. Why did I get here? I don't want this. I want something else. I said Cox-Mertz rule wiki. Oops, something's going on here. So it's good to know kind of what that is. This guy will give me what I want. I keep my keyboard sticking, I think. Oh, it's just me. One or the other. I guess there isn't this Rio thing, so maybe this is a little bit buried. Maybe you guys should write a wiki page for it. But anyway, it's just like frequency and time go together. I mean, you can swap them to the other. And then I said, I already told you intrinsic, and then the sequence of steps. Isn't that the same? Oh, this is the sequence of steps for the, what's it say? This is, he doesn't give this exactly. You have to figure that out. Time-dependent creep curve blends to fit the frequency data. These might be the same question, B and D, I'm not sure. Why is the molecular weight distribution needed? So anyway, if you answer D, you'll get B. So those are all tied together. So it isn't like an in-depth. Well, actually, the first question is a little bit involved, right? So, and then this one is a hypothesizing thing. And then the others, it's kind of a fairly straightforward paper, in my opinion, but basically it's pretty imposing because it's got like a couple mega equations in it that kind of makes sense, but you don't know exactly where they came from. Like this thing I haven't seen before, but if you ever need to model a molecular weight distribution, that might come in handy. It's just an empirical function someone made up, as far as I can see. He doesn't give example values for A, B, whatever. But it could be almost like a Gaussian if this B was 2, that would be a Gaussian. And then it's got this weird, this is almost like the Debye charge thing. It would be like 2 here, or it's exponential of the distance, and it's divided by the distance here. So these equations start to look the same if you look at them enough. And this is just empirical. Like they just tried till they got it to look like a molecular weight curve. I think this is it's a log here. So it's a log. If it's bell-shaped on a log axis, it's a log normal distribution. So this is a log normal function, I guess. No, it's log of the weight gives you the molecular weight. But anyway, so that's about it for this. I don't know hopefully you can do this. And then I haven't graded any of the other stuff, so I'm going to do it over break, like pile up all that grading. So I think I'm just behind the one homework plus this one. Oh, this one will come in after break. So it's due on like Thursday, Tuesday. And if you need more time, just say, but basically, hopefully we can get this. It should be a fairly short one, So anyway, yeah, next thing I just go through some like race gyration, hydrodynamic radius, like measures of polymer size, like experimental measurements and what they are, how you get them. A little bit about scattering, and then do some other stuff after that. I think that's kind of the end of like formal subjects, and then I'll go into I don't know. There were a lot of talks at this thing on plastic, like microplastics in the environment. That might be a good thing to do. Or maybe tie that in with something about waste streams and things. Might do a week on that. And then there were a bunch of things on again, like machine learning type stuff. And so one guy at Rutgers is doing machine learning with drug compounding. you know, expients they call it. So you have the drug and then you have to put in all kinds of stuff to make it work, right? And then how do you figure out what to put in, and then use machine learning to do that. And then he wrote like a review paper that's got an example, Google, like the Google, what is it called? Google something. Google has a place where you can do like Python code, you know. Colab, yeah. All right. So he's got a Colab web page to train you how to do machine learning for that particular thing. So I might just do that for 1 week, like go through machine learning on data analysis for product development, and then use that as the homework that week. Like go through his Colab thing. And he claims it's like simple, any idiot can do it. So we'll see, you know. So I don't know how many weeks we have left. We could also do like I've done this molecular dynamics simulation thing is similar to that. A guy wrote a thing where you can just work through it, but I used it in this other class, the thermal class. So, but maybe it's all right. They probably won't complain. No, anyway, a lot of the grads don't show up for this class anyway, so it's like tough, you know. But I think you guys would enjoy doing that. It's pretty fun. Like you download the LAMP stuff from the Sandia National Lab, you know, and then you just can run the code to do the simulation of like things sticking together, basically, bio things. But so that's probably enough. Those three things will probably be. I think we just have 2 or 3 weeks after break. I don't remember. Anyway, so there's plenty of stuff to cover. Like 5 after break. Oh well, then we have plenty of time for that. Is it? Just seems like it seems like it goes by. No, do we? Because it's already the teens, right? That's 8. 1 week in March. 1 week in March and 2 weeks.
Yeah. 5 more weeks.
Okay. All right. Well, yeah, I got plenty. But we can do all those things. And maybe if you guys, I can work up slides for whatever. Yeah, so anyway, yeah, why don't we quit there today? So have a good break, do something fun if you can, or work, you know.
Headquarters.